Modeling. It's the first event that we are organizing as the Center for Data Learning and Decision Sciences. AI is one of the most important scientific events that we are living through. It's transforming the world we live in, and weather and climate modeling are the most important problems that we are facing as a community, as the world at large. So it's a very timely event, and we are very happy to have put this together. We have some of the most eminent speakers within the country and some from abroad. So it should be a very exciting event. It's also, indicative of the kind of activities that we are pursuing at the center. So I'm hoping through this event, a vision emerges on many of the problems that we'll be working on in the coming years. This is, the center itself has a number of areas that it plans to work on. Machine learning, at the intersection of machine learning and financial modeling, that's one area. Weather and climate modeling is another area. Epidemiological modeling and reinforcement learning. So this fits into the broad, all of these are kind of areas where data science, extracting information from data is critical. And weather modeling is certainly an extremely important component of what we do. So we are very thankful to our speakers who've come here today. I'll first request Mr. Gautam Menon to introduce our first speaker, Dr. R Krishnan.
Thanks, Sandeep. And on behalf of Ashoka, let me welcome all of you. It's nice to have the first flagship event of the Center for Data, Learning and Decision Sciences, a name I like because it spans the whole range between sort of input to output and what one should be doing with the data once gets it. It's an honor to invite Professor R Krishnan to Ashoka, to welcome him to Ashoka.
Thank you, sir.
He's, of course, the director of the IITM in Pune. He was director 2 years ago. He became director 2 years ago. He's been there since 1995. He did a PhD from PRL Ahmedabad with Professor Keshavamurthy, and then spent time in Japan and other places before returning to IITM, where he had the Center for Climate Change Research. And that's particularly important because it developed India's first global climate model. And that's certainly an important strength to the indigenous effort in climate modeling. He's been a lead author in the IPCC reports on the summary for policymakers and various amounts of very important policy documents. It's an honor to have you here, sir. And I look forward to your talk.
Thank you. First of all, I would like to thank Professor Gautam Menon for the very kind introduction. Thank you, sir. And also Professor Sandeep Juneja for inviting me to Ashoka University. And also nice to see my former friend and colleague, Dr. Rajivan. And nice to see all the young people, young participants. So, today's, can we put on slideshow? I thought I will talk about, I'm not going to really talk about AI/ML because I'm not an expert in that. I'll talk something about weather and climate models. And I will talk because with climate change is happening, we are seeing all the extreme events, especially in the summer monsoon time, which is becoming one of the big problems. And I just want to tell that what are the lessons we have learned so far and what is the way forward. This is a talk I gave in JUX. Some of the slides are from the JUX Open Science Conference in a plenary talk. So just to give a brief, I'm sure many of you may be aware, but just as a repetition. So weather prediction, it has a big history, and numerical weather prediction, we call it as NWP. And the weather and climate model, the idea, almost the basic ideas were developed more than a century ago. And this was by Professor Wilhelm Bjerknes from Norway. He actually said that weather prediction should be based on well-established laws of physics and regarded as a deterministic problem. And so he conjectured that if you have sufficiently accurate knowledge of the atmospheric initial state, and this should be possible to predict the future states. This was in 1904. It's basically weather prediction is an initial value problem. You should know the initial condition of the atmosphere, of the ocean, you can predict it. And actually there were attempts during the First World War by L.F. Richardson to solve these equations numerically, because computer was not there. By hand he tried to do this for the surface pressure chart. And he also made important contributions to understanding the turbulent eddies and so on, L.F. Richardson. And actually, his solution was actually a failure. He had developed it for a small region. But later on, why the solution failed, it was recognized later. And over a period of time, people started understanding this, making measurements of the atmosphere using radio sondes, so they could get the vertical structure of the temperature and the winds and so on. And also satellites came in the 70s, and they were all used to produce the initial condition, which is required for weather prediction. And also people began to understand the atmospheric dynamics, better understanding. And to solve these equations, numerical equations of the laws of physics, you cannot solve it by hand. I will show that. So you will have to use numerical approximations, finite difference methods. So various stable schemes were developed. I think the big important one of the steps was the ENIAC computer, the first computer that came in the University of Pennsylvania. And so these were big giants, Jules Charny, von Neumann. He was a great mathematician and a pioneer of computer. And he was a polymath. And Fjordtoft, they actually produced the first numerical integration of the barotropic vorticity equation. This is a one-layer model of the atmospheric circulation. You can use it to, they made a numerical simulation for a few days. This is known as a quasi-geostrophic approximation. I'll not go into those details. They said that if you can eliminate in your initial condition the sound waves and the gravity waves, these are very fast-growing waves. So if there are some errors in the initial state, the errors will amplify very fast. And so you may not be able to predict accurately the large-scale waves or the planetary waves because they are going to corrupt them. So this is the problem that L.F. Richardson actually faced, because he did not eliminate the gravity waves and the acoustic waves. So which later on they developed techniques how to filter out these sound waves and gravity waves. And so we had the first numerical model of the atmosphere, and thanks to the computer, this was 1950. And the first successful real-time weather forecast was by Rossby and team in 1950. Actually, but this was just a area just for it's a beta model, beta plane model, not a full global model. And then another big giant was Norman Phillips. He generated the first general circulation of the atmosphere, a numerical experiment. He could predict the monthly and seasonal pattern of the tropospheric circulation. And this was the beginning of the general circulation models and climate models. And later on, this was taken over by Geophysical Fluid Dynamics Lab in Princeton. And they went on to do climate modeling. That was the beginning. And over a period of time, I'll come to that about the climate model itself. Now we are talking about the weather models. Powerful electronic computers came, and they could do all the massive calculations, and computing power increased. And so when I say basically the principal laws of physical principles, we go back to Newton's law, the giant. So these are all what is known as the Navier-Stokes equation. We have the momentum equation, which is basically the second law of motion. And so you will see that this term is the Coriolis force term. You have the acceleration term, the total derivative. And it has, of course, when we talk in space and time, you will have partial derivatives. And this is the Coriolis force term, which is important because you have a rotating platform. And these are related to the pressure gradients. And these terms here, F, these are the frictional terms. This is basically indicating the transfer of momentum by the eddies and how to represent them. So I'll come to that. Yeah. And we have the thermodynamic energy equation, basically, which is the first law of thermodynamics, is the energy conservation principle. And this term here that you see on the right-hand side, these are where all the processes that can lead to temperature due to diabatic, we call it as diabatic heating. It could be in the form of sensible heat from the surface. It could be in the form of latent heat due to the condensation of water vapor to form clouds, which is very important in the tropics. And also many atmospheric constituents, they can trap the long wave radiation like water vapor in the atmosphere. So all these terms, they can contribute to this heating term, which is a very important component of the thermodynamic energy equation. And you have a mass conservation equation, what we call it as mass continuity equation. And generally in the large scale, we assume that the atmospheric is in hydrostatic balance. which is this is also a part of the momentum equation, but we drop the vertical acceleration. This is very important, having the hydrostatic balance for getting the large scale structure. And lastly, the water vapor equation, changes in the atmospheric water. This is a very complex, especially for tropics, it becomes very important because we have the sources and sinks of moisture. There could be a source of evaporation from the surface, and also precipitation is also part of the term, yes. So, and water vapor is highly variable in space and time. So these are the basic equations. Then this is basically we call in the literature as Navier-Stokes equation. But then along with that, we add the water vapor equation also. Yeah, that's also part of that. Yeah, we have to have mass conservation. That's also part of this one. And then we have to assume hydrostatic balance. So the question is now because you cannot, these are all partial differential equations and they are coupled to each other. And so there's no way you are going to solve them analytically. And so basically what you do is when you try to solve these equations of motions, equations of motion, laws of thermodynamics, we are trying to predict the rate of change of temperature, pressure, velocity, humidity, so on, with time. And then you want to discretize them on a grid, and you have different layers in the atmosphere. So if you make the grid smaller and smaller, you are going to increase the resolution. Your time step is also going to get small. So typically, if you double the resolution, basically your computational cost is going to increase fourfold. So typically models use something like a 10-minute time step starting from an initial condition. And you have basically millions of equations. And now this resolution is even getting finer and finer. And in the 90s, the resolution in the atmosphere was about a 270 by 270 kilometer grid. Present day, it has reduced. Even now, we are able to run our IMD forecast model at 12.5 kilometer global model. And so that's because of thanks to the computing. And we have about 64 vertical levels in the atmosphere. And this is just the atmosphere. Now, if you want to couple it with the ocean, because when you want to go to longer time scale for a seasonal, or when you want to do climate change, you have to couple to a ocean model as well as a cryosphere. So your computational complexity is going to really increase. And as I said, some of the physical processes that are happening within the grid, what is called as a subgrid scale process, that you cannot resolve because the variables that I showed, they're all on the grid points, but there are processes like very convection, deep convection, which may be within the grid itself. And or there could be how the turbulent diffusion of how these eddies are going to transport heat and moisture and the momentum from the surface above. So these are subgrid scale processes, and these eddies are very efficient way of transporting so they can be from the scale of a millimeter to about a kilometer, but they are very efficient way of transporting the fluxes from the surface into the atmosphere. And you have also the radiation, the solar radiation, which comes, much of it, about 30% is reflected, 70% passes through the atmosphere. It heats the land-ocean system, and then it is radiated back in the long wave. And this long wave can be trapped by water vapor clouds. And so these processes, physical processes, they cannot be resolved, and so they have to be parameterized in terms of the large-scale variables. So various physical parameterizations are being used. So now this famous work by Lorentz, he had a simple model of the convection in the atmosphere. He had 3 equations with 3 variables. And what he found, these are nonlinear coupled equations. And there are some parameters, R and B and so on, sigma. And what he found out was, because it's an initial value problem, if I make slight changes in the initial condition, what will happen to the state of the system? So, so he discovered that even if you can see that these are 2 different, the forecast based on 2 slightly different initial conditions. After some time, they start diverging, although in the beginning they are together. And he told this is a plot showing it's an indication of temperature field. it can go from you start from one initial condition, it keeps going in this kind of trajectory. This is a phase-space system. You change a slightly initial condition, it can go to a different state. So this type of regime changes can happen. And so these are it's a deterministic equation with, so almost perfect initial condition also if you are having. He told after a certain period, finite amount of time, you lose this skill. This is this big discovery. And he called it as, so there is a limit of predictability. And at that time, the skill of prediction was only 2 days. And people thought, sorry. Yeah, but because when we go to climate and you want to look at processes that are beyond, let us say, a month or a season, the ocean becomes a very important component. You cannot restrict it to the just the atmosphere. And many of the things are, there's a phenomenon called as El Nino Southern Oscillation, some changes in the ocean temperature in the Pacific that can affect the circulation patterns, precipitation over the Indian region. And
What is the width that you take of the ocean layer?
yeah, ocean layer, top layer maybe about, usually in the top layer it's well mixed. We call it as a mixed layer. That can vary from 50 meters to 100 meters and so on. So the top layers are very, very small. It could be 5 meters, 10 meters and so on. And you go to the entire depth of the ocean. It could be as deep as 5,000 meters, 4,500 meters or so. So when you go to the deeper layers, the depth becomes, but not much happens. So those are on very long time scales, maybe thousands of years, or the deep ocean becomes important. So for the seasonal time scale, only the top layers of the ocean become important. Yeah. So, yeah. Yeah. Yes. Including the oceans. Yeah, but that model is just an atmospheric model. The sea surface temperature is prescribed. Because we are typically looking at few days. We are not about 10 days forecast we do. We don't go into the season. So the moment you go to the season and beyond, then you have to bring in the ocean. The ocean dynamics is, yeah. Yeah, they are doing in, day out. I think it takes few hours to run, get the 2 hours, 2.5 hours. Yeah, and yeah, because, yeah, very powerful computers and yeah. So basically, he set a limit of predictability, a theoretical limit of predictability up to 2 weeks, and this is mostly for the extratropical systems. So this I'm showing what is the current state. This was in the 1960 and by Lawrence, 1963. And now this is one of the famous weather, this is a leading weather center. And we have one in India, the National Center for Medium Range Forecasting. European Center started in 1979, and they focused heavily on the data assimilation because the initial condition is going to be important. And this is a way of combining various observations from various platforms, from balloons, from satellites, from ships, ground-based observations. And so the model keeps making, there's a kind of forecast trajectory by the model. Then you have intermittent observations coming at different times. And there's a way of combining these data, observations and the model to produce what is known as the analysis. And then you keep forecasting it. So this entire cycle keeps on going. And over a period of time, satellites have improved, more observations are coming. Earlier, the southern hemisphere was poorly sampled. Now even the southern hemisphere, because a lot of oceanic area in the southern hemisphere, but now more observations are coming even in the southern hemisphere. So what is shown here is this kind of a skill score, and how the skill score of this is a parameter known as the 500 millibar height. This is typically for the mid-latitude, how circulation, how good we are in predicting the mid-latitude circulation. And what this yellow line, so this blue lines, one is for the northern hemisphere, one is for the southern hemisphere. These are the skill of 3-day forecasts. The red is for the 5-day forecast for northern and southern hemisphere. Green is for 7-day forecast. Yellow is 10-day forecast. What it shows is now if you look at this is 80% skill score. Suppose you extend this 80%. So in 2020, suppose we are getting a 80% skill score. This, in the 7-day forecast, this was there, similar thing in 1990s we were getting in the 5-day forecast. And when you go back to the 3-day forecast, this was in the early 80s. So the skill of the forecasting, you are getting a longer lead time thanks to the data assimilation. So continuously they are making improvement in the skill of the forecast. And it's not only extratropical circulation, many features of the tropic, because in the tropics it's all dominated by the convection and the clouds. And we have these satellites like the Meteosat, our own INSAT. So they're giving this snapshot of the cloud movements, and models are also able to get this very large scale organization of the clouds. But within the inside, how the mesoscale convection develops, still there are issues with that, and which is becoming one of the challenges. So models have improved over a period of time, and this was a very nice paper that came out by Bauer et al. The NW numerical weather prediction is a success story, basically. What started, they say this computational problem, weather prediction, is comparable to the simulation of a human brain or the evolution of early universe. And this is performed every day, day in, day out at all the major centers across the world. And this has become a big success, actually, and it has been, although many other fields are like they have the aura of fundamental physics breakthrough, this is also a very quite revolution that has happened. And so this, and this is a very, and now people are not just looking at just from one initial condition. There are ways to perturb the initial condition if you have an initial state. So you can generate an ensemble of initial condition and an ensemble of forecasts. Then you can use probability method to say what is the probability of precipitation over a certain region. So this is becoming very popular even for the tropical cyclones and so on. And so this is I thought I'll show something from our own NCMRWF recently. So tropical cyclones we have done very well. So the problems in the Orissa super cyclone in 1999, about more than 10,000 people died. But now our skill of tropical cyclone prediction we have improved, and it's in single digit or maximum double digit, less than 20 deaths we see. And this was a typical example of a system in Gujarat that it produced heavy rainfall during 26th to 28th. And there was a low pressure system that went from, I'll show in my next slide, and that was producing this heavy rainfall. The model forecasts are able to get that. And simultaneously, a little later, another system was forming. And this actually went on to become a tropical cyclone later on, which eventually weakened. So weather prediction is a success story. Now what about it doesn't now stop there. Other problem that is what we are seeing is the climate has been warming, and this is the 2023, the global mean temperature had crossed 1.5 degree above the pre-industrial. It's all mainly because of the human activities, only because of the greenhouse gases like carbon dioxide and methane, which are absorbing the long wave radiation. And so with climate change, and of course when you go to the climate change, science of climate change itself, it started with Joseph Fourier in 1824, he was talking about the glass bowl effect, how these greenhouse gases can trap the long wave radiation, and it can warm the planet. Then John Tyndall. I think one important contribution came from Svante Arrhenius, a Swedish scientist. In 1896, he quantified the change in surface temperature to be expected from doubling of carbon dioxide. He predicted it would be about 5 degrees. He did not have moisture. He did not have convection, vertical transport of heat in this one. And subsequently, and also observations began by Charles Keeling from Mauna Loa from the 50s. They were able to make very precise measurement of the atmospheric concentration of carbon dioxide, methane, and greenhouse gases. It's still going on. This is known as the Keeling curve. I think a fundamental breakthrough happened by Manabe and Strickler in 1964. They said that vertical convection is very important. It's not just the radiation. So the moisture, how the moisture feedback happens. So they developed a radiative convective model to compute the thermal equilibrium. And 1967, they went on to, this was the paper that won the Nobel Prize and in physics in 2021. And they also had an experiment where they doubled the carbon dioxide and they showed that that could amplify the warming, just not just the carbon dioxide, water vapor feedback is going to. And so this was a cutting edge, this was 1967, and I had the good fortune of working with Suki Manabe in Japan. He was my boss. And so this is the 2021 Nobel Prize with Manabe and Klaus Hasselmann, they shared it. And also the Giorgio Parisi for the disorder and fluctuation of the physical systems. So the important contribution of the radiative convective model he introduced, how the radiation, convection, and water cycle can influence the climate and the it was and one more important contribution. This is Manabe at Princeton, and his boss Smegeransky, who started the GFDL, the first founding director. And so this is a paper from the Nobel Prize committee. So at the surface, you see in the troposphere, as you go up, the temperature decreases with height, and in the stratosphere, it increases with height generally, the normal. So with global warming, the troposphere gets warmed up. Also, the surface temperature increases. But in the stratosphere, it actually cools. That's the important thing. And now, discovery that he pointed out, and now people are able to see this in the satellite data. Yeah, now, of course, then periodically you have assessment of climate change assessments. So the 6th IPCC assessment report has clearly told that the warming that we are seeing since the 19th century, it cannot be explained just by natural variations. So the human has really increased, the human influence has really contributed to this warming. I will not go into the details. Yeah, so if you want to study climate change in its full complexity, you cannot just stop with atmospheric model. You need the ocean, and because you're really talking about longer time scales, you also have to have the carbon cycle if you want to see all the biogeochemical processes, both in the land and in the atmosphere. And there are also changes in the atmospheric composition due to aerosols and chemistry. And also there are changes in the glacier melt, and they can in fact affect the sea level rise and so on. And so if you want to really look at all these different components of the Earth system, you really need to go to the Earth system models, which is fundamental for studying climate change and also their impacts. And so basically they provide information about the physical, chemical, and biological mechanisms governing the rates of elements of the Earth system. And we know that this is again from the IPCC assessment that these are different future projections of the global surface temperatures. Right now in 2023, we are 1.45 degree compared to the pre-industrial. And in the future, the warming is projected to increase. These are different scenarios. This is a kind of very high emission scenario. SSP, these are what are known as shared socio-economic pathways. I'll not go into those details. These are very high emission scenarios where you can cross the global mean temperature could increase more than 4 degrees. And this is a very sustainable pathway, the SSP 129 and so on. Right now, we are somewhere in the middle of the road, this SSP 245. This itself, we will cross the 2-degree warming by end of 21st century. And one of the consequences of this increasing temperatures is that the patterns of, warming pattern is not uniform. It has most of the warming is concentrated in the polar region, in the high latitudes, but tropics are also warming. And these are from the model's projections, and this is the observed warming, present day. And associated with warming, the precipitation is also going to increase in many of these areas. But also the areas in the subtropics, the deserts, where the air actually sinks, they are going to get drier. So the variability of the precipitation is going to increase. So the wet regions are going to get wetter, and the dry regions are going to get drier. So the variability is going to increase. So that means some of the areas which are drought-prone areas, the drought could become, the severity of the droughts will increase, and so on. And one of the consequences, why I'm going to this thing is, the water vapor feedback is a very important mechanism, because as the temperature increases, the water holding capacity increases. And with every 1 degree warming, it could be anywhere between 6 to 10% of water vapor increase. So the direct consequence of that is the heavy precipitation increase, events will increase. And typically so the extreme temperatures are going to increase both in frequency and also intensity. and also heavy precipitation over land. And with a 2-degree warming, we can have a 14% increase in the heavy precipitation increase. This is just by thermodynamic argument. But now what does it mean for the monsoon region? It's a much more complex issue now. It may not be simple Clausius-Clapeyron equation. Because when you look at the monsoon precipitation itself, this picture, it shows the regions of rainfall, seasonal rainfall more than 100 millimeters, 100 centimeters per season. You can see along the Western Ghats, central India, and also the foothills. And these are produced by various systems like the monsoon low pressure systems, depressions that form in the Bay of Bengal move west. And there are also some systems known as MTC over Gujarat they can produce. And there are these cloud bands moving from the ocean to the towards the Indian subcontinent. So there are different time scales, different time and space scales. So it's a multi-scale interaction that is what gives rise to the monsoon. Now, I'll give some examples. That's what I want to quickly go through some of the events, heavy precipitation that we have seen. The June 2013 Uttarakhand event, which led to heavy rainfall and floods over the Himalayas. And this was a kind of interaction between the monsoon and extratropical circulation. Then also about the late 2010 flash floods. These were mesoscale convective systems over the high terrain of Leh Ladakh. And heavy rainfall over Gujarat and Western India. These are the monsoon rainstorms. We did some work. And I will also talk about the July-August 2022 floods devastating floods in Pakistan and Upper Indus Basin. Just these examples. And this was a huge disaster that happened in Uttarakhand in June 16th of 2013. And we looked at this paper by Vellore et al. And the Shiva statue was badly damaged at that time. Now they have kind of improved, they have made it all right, they have repaired it. So we looked at 34 such cases of these events in that region. And it turns out that during this period, there was a kind of early monsoon onset and a low pressure system